In December 2020, one number spread everywhere. Pfizer's vaccine was reported to be 95% effective. That number appeared in news headlines, policy discussions, and everyday conversations. It sounded precise and reassuring, even though it comes from data with uncertainty. At that moment, people were desperate for reliable evidence. Governments, clinicians, and the public were trying to understand whether the vaccine worked and how strong the evidence was. But that number did not appear by magic. What was behind it? To answer that, we need to look at how the evidence was produced. In the clinical trial, researchers compared COVID-19 cases in two groups of nearly equal size, 21,720 in the vaccinated group and 21,728 in the placebo group. There were 8 cases in the vaccinated group and 162 in the placebo group. These results were published in the New England Journal of Medicine, a leading medical journal. From these data, researchers estimated vaccine efficacy at 95%. Strictly speaking, the New England Journal analysis is based on incidence rates, but because the groups are nearly balanced, this simpler calculation gives essentially the same result. But the paper did not report only the point estimate. It also reported a 95% confidence interval from 90.3 to 97.6. Now here is the question. How should we interpret that interval? Is it correct to say, there is a 95% probability that the true vaccine efficacy lies between 90.3% and 97.6%? That is the central question of this video. If you think you know the answer, test yourself with the quiz at the end. I'm Jose B., the traveling medical data scientist. In this video, we are going to unpack what a 95% confidence interval actually means and why one of the most common interpretations of it is wrong. And this matters for more than just statistical vocabulary. It affects how we interpret evidence in real studies, including ones that influence medical and public health decisions. Confidence intervals are used to summarize evidence in medicine and public health. If we misinterpret them, we risk misunderstanding the strength of that evidence and making poor decisions. With that in mind, let's return to the Pfizer interval and ask what it actually means. How should we interpret the Pfizer confidence interval from 90.3 to 97.6? A common interpretation is that there is a 95% chance that the true vaccine effectiveness lies within this interval. Before we assess whether this interpretation is correct, it helps to see how widespread it is. In a study by Hoekstra and colleagues, both students and researchers were asked to evaluate 6 statements about confidence intervals. On average, each group endorsed more than 3 incorrect statements, even though all 6 statements were false. So this misunderstanding is not rare. People tend to interpret confidence intervals as probabilities by default. But why do people default to this interpretation? The true value is unknown. We compute an interval from data, and probability is the language we typically use to describe uncertainty. It is therefore tempting to interpret the interval probabilistically. However, this interpretation is incorrect. To understand why, we need to be precise about what is random and what is fixed. To answer that question, we need to step back and ask a more basic one. When is it appropriate to use probability at all? Probability applies only to quantities that are random. Before we observe data, outcomes are uncertain, so probability is appropriate. But once the data are observed, the values are fixed. At that point, statements about the data are no longer probabilistic, they are simply true or false. Now, apply this idea to confidence intervals. Before observing the data, the interval we will compute depends on the sample, so it is random. But once the data are collected, the interval becomes fixed. The true vaccine effectiveness is also fixed, even though we do not know its value. All the randomness comes from the data generating process. This leads to an important conclusion. The 95% refers to repeated sampling. It does not refer to this specific interval, and it is not the probability that the true effectiveness lies in this interval. Now that we understand where randomness comes from, we can look at how confidence intervals are constructed. A confidence interval often has the form sample estimate plus or minus a margin of error. The estimate, also called the point estimate, is the sample vaccine effectiveness computed from the data. In the Pfizer trial, that value is 95.0%. The margin of error has 2 parts, a multiplier, in this case a z value, and the standard error. The standard error describes how much the estimate would vary if we repeated the study with different samples. That is the key idea. A large standard error means the estimate would vary more from sample to sample, so the interval must be wider. A small standard error means the estimate is more stable, so the interval can be narrower. For the standard normal distribution, about 95% of values lie between minus 1.96 and 1.96. That is why z equals 1.96 is commonly used in confidence intervals based on normal approximations. Now, imagine repeating the study many times. Each sample would produce a different estimate and a different interval. This repeated sampling perspective is what explains the meaning of the 95%. There is one more detail worth noticing in the Pfizer example. Many confidence intervals have the form estimate plus or minus margin of error, but the reported Pfizer intervals is not exactly symmetric around the point estimate because it was constructed on a transform scale and then converted back. Also, there are two different 95% here. The first, 95.0%, is the sample estimate of vaccine efficacy. The second, the 95% confidence interval, refers to the long-run success rate of the method. They are not the same quantity even though the number 95 appears in both. This numerical match is coincidental. To avoid confusion between the 95% confidence interval and the 95.0% sample estimate of vaccine effectiveness, we will use a 99% confidence interval. I show the details of the calculation here. I construct this 99% confidence interval using the same method as in the New England Journal paper, based on the binomial model and the Klopper-Pearson construction. You do not need to follow every step. The key result is that the 99% confidence interval runs from 87.6 to 98.5. Notice that this 99% confidence interval is wider than the 95% confidence interval. This is not a coincidence. Increasing the confidence level requires a larger margin of error, so the interval must expand. Where does the 99% confidence level come from? It comes from imagining that we repeat the study many times, each time collecting new data and constructing a new interval. Across those repeated samples, we obtain many different intervals. About 99% of those intervals would contain the true effectiveness. This 99% refers to the method, not to this specific interval from 87.6 to 98.5. The 99% does not represent the probability that this interval is correct. So when we say we are 95% or 99% confident, we are describing the long-run performance of the method, not making a probability statement about this particular interval. To make this concrete, I will show results from a simulation with 100 repeated samples, each matching the sample sizes from the New England Journal clinical trial, about 21,700 people in each group, assuming a true vaccine effectiveness of 97%. We begin with 95% confidence intervals and later increase the level to 99%. In each repetition, we take a fixed size sample from the population, calculate the vaccine effectiveness, and construct a 95% confidence interval. On the screen, each horizontal line represents one interval. The dot is the estimate, and the line shows the range of plausible values based on that sample. The vertical green line marks the true vaccine effectiveness, which in this simulation is fixed at 97%. Now notice what happens. Most of the intervals cross the green line, but not all of them. A few miss it completely. Those are shown in red, and there are 5 of them. This is exactly what a 95% confidence interval is supposed to do. If we repeated this process many times, about 95% of the intervals would contain the true value of 97%, and about 5% would miss it. In this simulation, 5 out of 100 intervals, or 5%, fail to contain the true vaccine effectiveness, not because anything went wrong, but because the method itself allows that level of error. Now let us repeat the same experiment using 99% confidence intervals, keeping everything else the same. Notice what changes. The intervals are now wider. That is the cost of increasing the confidence level. In exchange, almost all of the intervals contain the true value, and only a very small number miss it. In this simulation, only one interval fails to capture the true value of 97%. This is exactly what a 99% confidence interval is designed to do. If we repeated this process many times, about 99% of the intervals would contain the true value, and about 1% would miss it. By increasing the confidence level, we reduce the chance of missing the truth, but only by accepting wider intervals. That trade-off is unavoidable.
In practice, we take one sample and compute one confidence interval. Once computed, that interval is fixed. It either contains the true value or it does not.
This repeated sampling interpretation was formalized by Jerzy Neyman in 1937. His framework answers the question we raised earlier. If the true value is fixed, where does probability come from? In this framework, the true value is an unknown but fixed number. It does not vary from sample to sample, so probability does not apply to it. Instead, probability describes how the method behaves when we repeat the study many times. Each time we collect a new sample, we get a new estimate and a new interval. Some of those intervals will capture the true value, and some will not. The key idea is that the randomness is in the data we could have observed, and therefore in the intervals we could have constructed, not in the true vaccine effectiveness itself. So when we say 95% or 99%, we are describing how often this method succeeds over many repetitions, not the probability that this particular interval contains the true value. With that framework in place, let's interpret the 99% confidence interval from 87.6 to 98.5%. A common interpretation is that there is a 99% probability that the true vaccine effectiveness lies in this interval. That sounds reasonable, but it is incorrect. Once the data are observed, the interval is fixed, and the true vaccine effectiveness is fixed, so there is no probability to assign to this specific interval. Instead, we use the standard wording. We are 99% confident that the true vaccine effectiveness lies between 87.6 and 98.5%. But what does that actually mean? It means that this interval was produced by a method that, in repeated samples, would capture the true vaccine effectiveness about 99% of the time. At this point, you might wonder whether this limitation is just how statistics works, or whether there is another way to think about probability. There are two main approaches in statistics. In this video, we use the Frequentist approach because the results reported in the New England Journal of Medicine are based on that framework. Moreover, in the statistics courses you have taken, you have most likely learned the Frequentist approach. In the Frequentist approach, probability refers to long-run frequency. The true value is fixed, while the data we observe are random. This leads to confidence intervals, where the probability statement refers to the method, not to the true value. In the Bayesian approach, probability represents uncertainty about unknown quantities. The true value is modeled as random, and we update that uncertainty using data. This leads to credible intervals, where it is meaningful to assign a probability to where the true value lies. This is why a Bayesian can make a statement that sounds like the one people often try to make about a confidence interval, assigning a probability to the true value. But that statement comes from a different framework and different assumptions. So while the wording may sound similar, the interpretations are fundamentally different. Now we can see why so much confusion arises. The issue is not just technical, but linguistic. In everyday language, saying, "I am 95% confident," sounds like a statement about belief. It sounds like we are assigning a probability to the truth of a claim. So when people hear this phrase, they naturally import the everyday meaning of confidence into a technical setting. That is not carelessness. It is exactly what ordinary language trains people to do. But in statistics, the phrase 95% confidence interval uses the same word in a completely different way. So naturally people ask what they actually care about. What is the probability that the true value lies in this interval? That is a reasonable question. But confidence intervals do not answer it.
There is another way to see why 95% confident cannot mean a 95% probability that the true value is in the interval. Let us test that interpretation in extreme cases. Sometimes a confidence procedure can produce unusual intervals. For example, the interval might be empty, meaning it contains no values at all, or it might be extremely wide, containing almost everything. Now ask yourself, does the usual probability interpretation still make sense? If the interval is empty, then saying there is a 95% probability that the true value lies in it is impossible, because the interval contains nothing. If the interval is extremely wide, then the statement becomes almost trivially true, and the number 95% no longer tells us anything useful about that specific interval. So even though the probability interpretation may sound natural when the interval looks ordinary, it does not hold in general. That is the key takeaway. 95% confident is not a probability statement about the true value being in this interval. It is a statement about the long-run performance of the procedure that produced the interval.
Even when we interpret confidence intervals correctly, there is one important caveat. The stated coverage, whether 95% or 99%, relies on assumptions about how the data are generated. For example, we often assume that observations are independent, that the sample is representative of the population, and that the model we use, such as a normal approximation, is appropriate. If these assumptions hold, the method will capture the true value at the stated rate, such as 95% or 99%. But if they fail, the actual coverage may be higher or lower than the stated level. So the coverage level is always tied to a model, even if that model is not stated explicitly. At this point, you might ask, why does this distinction matter? Interpreting a confidence interval correctly is not just a technical detail. It changes how we think about evidence, replication, and decision-making. When confidence intervals are treated as probabilities about the true effect, results can feel final. Once the interval excludes the null, it is easy to treat the conclusion as settled. A more accurate view is that the 95% refers to the long-run behavior of the method. Each interval is one realization from a repeated process. This perspective also changes how we understand replication. When one study suggests an effect and another does not, it may feel like a contradiction. In the Frequentist framework, this is expected. Even well-conducted studies will sometimes produce results that do not align because the method allows for error. So apparent inconsistencies are not necessarily failures of science. They are part of how evidence accumulates over repeated studies. Finally, this helps avoid a binary view of results. It is common to think excludes the null means works, and includes the null means does not work. But confidence intervals contain more information than a yes or no decision. The width and location of the interval matter. A precise interval near the null may be more informative than an imprecise interval that barely excludes it. This brings us to the final takeaway. The true value we are trying to learn about is fixed. It does not change from sample to sample, even though we do not know it. Before we collect the data, both the estimate and the confidence interval are random. They depend on the sample we happen to observe, and different samples would give different results, but once the data are observed, that randomness is gone. The estimate and the interval become fixed numbers. They are no longer random quantities. This is why the 95% or 99% does not refer to a probability about this specific interval. Instead, it refers to the method that produced the interval. Over many repeated samples, that method will capture the true value at the stated rate. So the key point is this: the confidence level is about the procedure, not about the true value being in this particular interval. Are you ready for the quiz? This question asks whether you can apply what we have just discussed to a real published result. You are now looking at a finding from a clinical trial. Read each statement carefully and choose the one interpretation that is correct. As you do this, think about what is random, what is fixed, and what the 95% actually refers to. Feel free to pause the video to think about your answer. The correct answer is statement 3. This is the only statement that correctly describes what the 95% refers to. It refers to the long-run behavior of the method used to construct the interval. Now look at why the other options are wrong. The first assigns a probability to the true reduction, but the parameter is fixed, so that statement is not valid in the Frequentist framework. The second refers to this specific interval, but once the data are observed, the interval is fixed. It either contains the true value or it does not. The fourth confuses the interval with variation across patients. A confidence interval is about a population parameter, not individual outcomes. The fifth treats the interval as if it were a probability distribution over possible values of the parameter. That is not what a confidence interval represents. So, once again, the key idea is that the 95% refers to the method, not to the parameter. Interpreting confidence intervals correctly does not make conclusions weaker. It makes reasoning more careful, and helps avoid treating a single result as more certain than it really is. As the title of this channel suggests, I'm a traveling medical data scientist. Today, I'm sharing footage I captured in my home state of Georgia, a place with a remarkable range of landscapes. Where I live, I'm within driving distance of the mountains, where the scenery feels calm and expansive, and within a few hours, you can reach the ocean with its wide horizons and steady rhythm. Georgia also experiences all 4 seasons: each with its own character. In the fall, the landscape transforms as the leaves shift into shades of red, orange, and gold, creating a striking contrast against the sky. Georgia is also home to Atlanta, a major city with a very different kind of energy. It has played an important role in U.S. history, particularly during the Civil Rights Movement, and continues to be a center of culture, business, and transportation. For many years, its airport has been recognized as the busiest in the world for passenger traffic. That's all for today. If you learned something about confidence intervals, feel free to leave a comment. Thanks for watching. This is Jose B., the traveling medical data scientist, signing off.